company, and although their products are not in the market, but they're the first company who are able to show like a solid state battery with energy density which is almost like a 20% higher than conventional battery, which is safe. And but they are making on the single stack, they are trying to make is multiple stack to increase the energy density and for the real application. So this is the time basically where this is kind of a very race, I would say. Whoever will win the race, uh, will be the top in this basically the game. Okay, so just a brief introduction. We, as more and more we are getting dependent on the renewable energy, the storage is important. Without storage, the renewable energy is not a solution because it's the intermittent source of the energy. It's not a constant, the source of energy. Like, from sun, when the other part of the world sun shines, then the other part of the world is dark. Okay, and sometimes in maybe in Rajasthan or in maybe in Texas where the sun shines more, and the same time in London, maybe in the Delhi, maybe you have too much cloud or rain, so the sun doesn't shine much. Same for the wind. So basically, if you really need a constant source of the energy, and from the renewable source especially, then there is no alternative that you need a storage. Okay, the storage should be in the grid, in the form of grid, where basically you can store the energy, and then whenever according to your demand you can supply those. So the supply and demand should be balanced, and this balance happens by incorporating the battery into the system. So whenever someone although the cost of the wind and the solar energy went down almost 99% less for last 10 years, but still the main cost of this implementation of this solar panel or wind energy cost goes for the storage, because storage actually cost more for the installation, for the whole setup basically, rather than. And the other thing is like electric vehicle, like we are using still we are using fossil fuel, like for our vehicles IC-based engine. If you really want to conserve this fuel, and then we have to electrify the vehicles also. I mean, at home definitely you can plug and play anything, you can get the electron at home, but in car how can you get the electron? That is kind of a challenging, and that's why the energy storage is important. So you have to let the reach electron in every point so that we can use the energy, and that is possible with the storage. We know there are various applications nowadays, from the lithium-ion battery, from like a drone to mobile, small consumer electronics to like a even the electric vehicles. But there are still not, this is a technology which is like a completely solved. There are many problems in this technology, which is mostly the energy cost, safety, and the sustainability, which I'll briefly talk a bit more later. But one thing, if you see from the 2010 to 2019, the cost of the battery goes down drastically, where the per kilowatt hour from 1100 to it went down almost like a 156. Although you see the price of the lithium, I know that goes high. So although the price of the lithium goes high, the cost of the battery pack goes down, and that is happening because of the new chemistry is always evolving. So from the lithium manganese oxide to lithium cobalt oxide to NMC to NC, once we have the new chemistry evolving and the new cathode or anode evolves, then basically that increases the energy density also. So although the price of the lithium increases, the energy density increases more, and that's why the battery prices goes down. So if you really want to improve the performance of the battery and reduce the cost, then one thing we really think about how can we bring the new chemistry and cost-effective new chemistry into this technology. Now, one of the main concern, as well as discussing, is the safety. So we are using like a carbonate-based electrolyte with the conventional lithium-ion battery, which whatever we use nowadays in our car or in our mobile. But those are like a very low flash point, and then the battery can go like a you can see like a lot of accident happens with the mobile, laptops, and especially for the electric vehicles, and that is a huge safety concern, and which happens because of the shortening of the battery, and also the thermal runaway. The battery heats up and basically it explodes. and logically, like most of the company who actually manufactured the battery, and the 1 in 10 million battery actually can be explored. That is the kind of a statistics they need before to marketize the battery. So that kind of high quality of the battery needs to be made. And the other important thing is like when it's a small mobile or small laptop, maybe your the combustion or the blast is not that, explosion is not that strong. But when you consider a electric vehicles, like like when you are carrying like 1,000 18650s battery cells, it is equivalent to you are carrying like a 10 dynamite. So you can consider you are driving a vehicles with the 10 dynamite. And the whole battery management system is more complicated. If you have a single cells, is quite easy, but when you have a multiple cells, there are voltage, current calibrations, and then the how do you the how do you take the power from the from the lot of different cell distribution of this power. These are more complicated, so that's why there is always a risk factor in the battery technology. And then other thing is like the conventional, the lithium battery, whatever you are using, the 40% of the cost goes for the cathode. Battery have many components: cathode, anode, current collectors, separators. You have the battery case. You have the many things are there, electrolyte. But the 40% of the cost goes for the the cathode. And the main component of the cathode with the conventional battery is the cobalt. Cobalt is the one of the because of the cobalt, actually the lithium battery is so successful nowadays. Even if you consider the currently NMC 622, you still have 20% of the cobalt into that. Cobalt somehow stabilize the structure. Without cobalt is very safety hazard, and your capacity is also kind of, you won't get the theoretical capacity sometimes. So there are a lot of reasons why the cobalt is so important. But the problem is like most of the cobalt in the world has been stored in Congo. And then there are so it is not like equally distributed throughout the world. So this specially, and then that is something. And also there are 40,000 child laborers are working every day, and there are a lot of illegal minings are happening. So that is a problem. So nowadays people are working, trying to find out a new chemistry where you do not have to use the expensive toxic cobalt, which is actually localized in especially the Congo, which is like a also politically some zone, certain zone also. So that is something, one of the drawback of this kind of a conventional battery. The other bottleneck, I would say, like energy density, like conventional battery. So we use like a lithium battery in the range of 250 watt-hour per kg, and then with the commercial 85 kilowatt hour pack of the Tesla, we can go up to 400 kilometer. But this is not what we get on the IC engine. One IC engine, if we just full our fuel the petrol, we can go up to 700 kilometers. So there is always a ring anxiety that how can you increase the energy density of the battery so that a single charge you can travel up to like a 600 700 kilometers. Okay, and you need the robustness of your battery so that it can work any temperature. Nowadays, you always have to have very complex battery management system, and then that also costs a lot of your battery. And the battery components should be, chemistry should be such a way that it should work very low to high temperature also, so that your management system is not, a battery management system is not like a reduce the cost of this management system. Also the high power, the kind of high power you are expecting from your like conventional IC engine, the battery should provide those kind of power. So basically, if you see, we started with the generation 1 where the carbon, sorry, this is somehow different, the cathode, and then this is carbon anode, not the cathode, sorry, it was the use, and the energy density was around 250 watt-hour per kg. From that, right now there is a lot of success, and lot of people are working on the silicon based, replacing the carbon from the silicon, where you increase the energy density from like a up to 250 to 300 watt-hour per kg. Then if you again increase the energy density, nowadays this is the most challenging. People are trying to use the thin lithium foil, because carbon has a capacity around 370. Silicon carbon is depends on the composite, but mostly like 1000, 1200. But if you guys use the thin lithium foil, then basically your energy density is also increased drastically, because lithium has very high capacity. So you are increased up to 400 to 500 watt per kg. But there is in future directions, people are looking for the no anode. So basically cathode will have sufficient lithium, and you have a battery which will be working very highly efficient way. So the you don't need any anode at all. It's like anode free battery, which is very cost effective and extremely high energy density. There are very few papers and very few reports nowadays on the anode free battery, but this is some technology which may be the most dominating technology maybe after couple of years on the battery. The other most important is the sustainability. So you see, like from 2011 to 2019, there are almost like how much, like 5 million vehicles has been sold. Okay, and then every country from China to Europe to Korea, from every country, the electric vehicles consumption is getting increased. But then what will happen? This kind of huge amount of the battery. I mean, once these cars are dead after suppose 8 years or 10 years, and then what will be what is the what will do with all those batteries? Okay, we need to sustain for long time. So there should be such way these batteries are recycled. That's why that's the way basically we can sustain long and long. And for an example, if you see, if we consider the combustion engine in US, like it was 270 million combustion engine with the lead acid battery, and then from 270 from the million combustion engine, there is a 99% at the recycling rate. But if you see the lead acid battery, but if you see for the lithium-ion battery, there is almost 1 million plug-in electric vehicles in the US. There is only 5% is the collection rate of the battery, and from the 5%, there are almost 2 to 3% at the recycling rate. And this is give you a hint why the lead acid battery is such a the sustainable and such a successful battery technology. But the problem is the energy density of this battery is low. But if you really want to be the the sustainable like the lead acid battery, then we have to really think about how can we increase the collection of those dead batteries, either is from the small consuming electronics, or either is from the laptop, or more either someday actually will be come out all those like a battery waste, and which will be not really useful. And then even there is a lot of demand of this battery technology, there will be a lack of the raw materials. Okay. Because I'll come later to explain more. Now all this problem I have shown here, like a cost, sustainability, safety, and then whether the solid state battery can solve all this problem. Okay, now solid state battery is nothing, is very easy. Like your normal battery, you have a liquid electrolytes, you are replacing the liquid by the solid only. Okay, so one thing you can definitely think that is that like a replacing liquid which is flammable by into solid, you must have increased the increase the safety concerns. So solid state batteries are one of the important thing is doesn't have the combustion or the explosive tendency. So that's the way. If you are carrying a battery or if you are in a small electric in your phone or in your laptop or in your electric vehicles, basically you are safe. There is no way that it can explode. Also, the expected energy density of the solid state battery actually higher. I'll come to the reason why it is higher, but yeah, people are trying to make this, but it can go up to 600, and nowadays there are reports that there are 700 water per liter and energy density of the lithium battery reported into the literature in the academic from the academic institution. Okay, so it's not, this is also quite good.
Sir, sorry to interrupt.
Yeah,
Sir, the screen is not visible. Can you share the screen again?
Not. Let me share it again.
Thank you.
Can you see now?
Yes, sir.
Yes, Vic.
Yeah, thank you. So, yeah, as I was saying that the energy density of the solid state battery is also quite higher compared to conventional lithium-ion battery. Like there is an Toyota also made a prototype in 2020, which is 400, and very recently the Samsung made a prototype with the 700 watt per liter. So this is also like a very good news for the solid state battery technology for the small scale fabrications. And energy density also, it depends what scale, where you are actually looking for the energy density. I mean, the materials using for the solid state may are different from the conventional liquid based lithium ion battery. Also depends on the cell fabrication. The cell fabrication process from the liquid and the solids are different. The stackings are different. Even when you put the battery into the electric vehicles, okay, the battery pack are different. So every individual things, like from material, cells, pack to system, every cases the solid states could be different from the conventional lithium ion battery, and that makes the difference on the energy density, which I'll come later also. For an example, if you see like a conventional today's anode, we have a graphite and a cathode, right? And we need to have the very large quantity of the graphite, and volumetric also energy density is quite low because of graphite is low density materials. Now, if you have a solid state basically, then actually you can use the lithium metal. Normal, the historically, if you see the lithium-ion battery, the first lithium-ion battery was made with the lithium metal. It's not really with the graphite. And then lithium metal has a problem of the dendrite growth, and because of the dendrite growth, it has been replaced with the graphite. Okay, and the inventor of the graphite also got the Nobel Prize 2019. Akira Yoshino. Okay, but if we replace the solid state liquid electrolyte with the solid electrolyte, then you can use the lithium metal. So you do not have any possibility of the dendrite because you block the layer. Okay, so that is and then you come out with the extra place. From the extra place, you can put one more cell. So basically, see, that's the way you can energy density. Your capacity and the will be increases. Your voltage will increase. If voltage will increase is mainly because of you are using lithium. So anything versus lithium is the highest voltage compared to graphite. At the same time, with the same volume, you are using like two different battery cells. So you're reducing the mass also. So that's the way you can increase the energy density of the solid state battery. And then you no need to do the conventional battery cell lines basically that is which we normally used, like the slurry mixing and then casting, drying, like a line. And the same line also can be used for the solid state battery. So the existing lines which are used for the lithium ion battery can be easily converted to the solid state battery. You no need a totally fully a new architecture for the solid state battery. And there is an additional advantage of the energy density is that on a normal battery, suppose we have a 3-volt battery, right? If we want to make an output of a 9-volt, then we have to make a series connection of the 3 pouch cells, right? And then finally you get an output of the 9-volt. But in a solid state battery, you don't need that. You no need to make a 3 pouch cell and give a connection. What you can do basically, you can just stack one by one, and then whatever the desired voltage you wish, you can get output from that. And that is the advantage of this, like a solid state battery, that you can actually reduce lot of dead space. At the same time, you can increase the volumetric as well as the gravimetric energy density. There's an additional advantage is that, like normally the battery management system is always there with your electric vehicles, okay, and it has lot of different component of the battery management system, and then especially battery attached with the pump, and then pump with the expander, evaporator, compressor. There is a complicated systems is there, which makes sure your battery is functioning well and functioning well and safely also. And this is very important. So you have to have, and then to run this pump, evaporator, compressor, condenser, everything, the energy is coming from this battery only. Okay, so battery not only used for your driving the vehicle, for the drive, for the range you want. It's also helping to run the inner component, which is actually inside the battery component system. But in solid state, basically, solid state battery is something which can work very low temperature to very high temperature. Even high temperature, where the normal battery perform very worsely, solid state battery can work very good. So the motor can be directly connected to your battery. You do not have need or may or may not need very complex battery management system for the solid state battery. So that's why the whole battery power will give to run the motor only, and your like a range will be much higher, and your cost of the battery will also go down, because you will have the low cost battery management systems. That is also advantage of the solid state battery. I will come later. I will show why this battery, how does this battery work at high temperature. Give an example I'll give. Okay, now this is very in solid state battery. We are using the solid electrolytes, and the solid electrolytes have usually the ionic conduction happens through the Frankel or Schottky defect. I think most of the students are aware of this fact. Like when you have a pure crystal, you do not have a conductivity. You have to make a defect into your system to make it conductivity, basically. And there are few other things on which it depends. One is like polarizability. Like selenium is more polarizable than sulfur than oxygen, according to HSAB principle, like Hartzell acid-base principle. So if we increase the polarizability, basically, then actually reducing the activation energy of the jumping from one side to another side, because the environment on which it go through will be less polarizable. That means the ion experience the least coulombic charge, which reduce the activation energy. Cell volume is important. If you increase the cell volume, then your conductivity will increase. The defect concentration is higher. Defect concentration is nothing but the number of carriers. So as much as defect you can create into your system up to a certain levels, without like any phase change of the materials, mostly you usually have the conductivity increases. This is for an example. If you see the sodium phosphate, which is a very low conductive at 100 degrees Celsius, 10⁻⁸ Siemens per centimeter. If you just replace the oxygen by sulfur, okay, the conductivity increase almost 4 order magnitude. Can you see, like a Na3PO4 to Na3PS4 is a 4 order increment of the conductivity. And then what you can do, you can replace the oligovalent substitution or isovalent substitution. Oligovalent substitution created a lot of defect, sodium vacancy, okay, and then isovalent substitution, that will make either more polarizable moiety, or it can create the cell volume increases, and somehow the conductivity also increases. So these are the parameters we can play with to increase the conductivity of the solid electrolyte, because we need as much as high conductive solid electrolyte, which is close to liquid, to make the battery functional in solid state. There are different type of solid electrolytes, but mostly I would say oxide and sulfide, which is dominated into the market. And there are 4 key parameters are important. One is the ionic conductivity, electrochemical stability. Electrochemical stability is nothing but when a battery operates 4 volt, the electrolyte should sustain also at 4 volt. Mechanical compatibility. Okay, so it should be mechanically robust, so that battery is kind of a breathing system, so the volume changing happens in every cycles. Okay, so it have to have some mechanical flexibility, where it can compensate the volume change, basically, without forming any crack into the system. And also it should be air and moisture sensitivity, because we cannot afford like a globe box fabrication of the whole battery system. The battery usually been fabricated in the dry room. Okay, so the dry room sensitivity of this electrolyte also very important. If you see like the oxides ionic conductivity a bit less, electrochemical stability is very high, but the mechanical and the air sensitivity is also very worse. Mechanical, it is basically oxides, so they have very high young modula, and I'll come later. And then for sulfide use is a totally opposite, extremely high ionic conductivity. Even some of the sulfide electrolyte has the ionic conductivity which is equal to the liquid electrolyte, and extremely good mechanical stability. So mechanical formability means, like, at room temperature you can press it and you can make a battery normally in oxide you have to sinter at very high temperature to make a pellet. But sulfur given advantage, but the electrochemical and the air sensitivity of the sulfide is also extremely worse then. So it is kind of a like, you know, the which one do you choose according to your what kind of experiment, what kind of battery you want to really make. For example, if you see the LLZO, lithium lanthanum zirconium oxide, which is in the range of young moduli is 150 gigapascal, in the polymer is only 6 gigapascal, and this sulfides belongs to like a 24 gigapascal. So this material like a LLZO, if you heat it and try to make a pellet, if you see the surface ACM image, you have lot of grains. And then individual grains you can see. So basically there is always the grains are not merged together, and you have always lot of grain boundaries, and those grain boundaries actually reduce your ionic conductivity. But if you see the sulfide, this is the pressure, this is the density. Without heating, this is the heated almost like a 700, 800 temperature for LLZO. For sulfide, you just press it, and then you can densify only by room temperature pressing of like a 400 megapascal. You can densify almost 99% happens. And you see, once you densify, you are merging the grain together, and here you can see at the high pressure of 360 megapascal, you are almost merged all the grains, which is not possible for the oxides. That's why the sulfides is dominates on the market a lot of places, and they believe the sulfide is something is very useful for the coming battery technology. Battery technology. Here is also other parameter. I'm not going through all through, and the polymer is also included. But one of the most important thing is like the electrochemical stability. Like when you have a like large electrochemical stability, the homo-lumo gap is higher for your like a conventional liquid electrolyte. When you charge your battery, like you are increasing the potential between the anode and the cathode, then basically the oxidation and reduction and oxidation happens, and this is called the solid electrolyte interface. This is also cathode electrolyte interface happens, and then amount of this ACI form on the anode and cathode side, that will give a impedance, extra impedance into your battery system. Okay, now if you have a small amount of the ACI formation, that will give a like a the small impedance, and that is good for your cell. But if you have a very small homo-lumo gap basically, and then if you then automatically when the cathode and anode they will touch each other, there will be some chemical reactions, and when you charge your battery, then it will be an additional electrochemical decomposition. So you have a chemical reaction as well as electrochemical decomposition, which is very high amount if you can see compared to this much. Okay, and this is very important, and if this formation is larger and larger, that will create an extra resistance in your battery, and which is really not good for the battery. So the most important of the battery basically is like the the interface of the battery, like how much this ACI and the CI has been formation takes place, rather than what is the ionic conductivity of the battery. So people always try to find the high conductive solid electrolyte, but interface is the most important, because most of the resistance of the solid state battery is coming from the interface, either is from the chemical reaction, either is from the electrochemical reactions. Okay, for an example, give you an example of what happens. Suppose you have a normal, this is kind of a solid state battery where you have a lithium metal anode and you have a solid electrolyte, and this black one are the cathodes. Okay, and these are the current collector. This is the typical solid state battery with the lithium metal. Now, if we use the LGPS, which is the one of the highest conductive solid electrolyte, is 10 millisiemens per centimeter, higher than liquid also at room temperature. When it touches with the lithium metal, it will form Li2S, Li3P, and lithium germanium alloy. Now this is the insulator. Li3P is the ionic conductor. Now lithium germanium, which is from, it's an electronic conductor. Because of this electronic conductivity of this lithium germanium alloy at this interface, brown color, this interface always start growing and growing and growing. Okay, and grows until the full cell sorts. So even this is the extremely high ionic conductivity, this is the unstable and dynamic interface formation takes place until the cell short. It cannot use at all into the battery system. On the other hand, this is almost one order less ionic conductivity, Li6PS5Cl, and when it starts with the lithium metal, it will also from Li2S, Li3P, but along with that, it will from the LiCl, which is also insulator. So none of this component is the electronically conductive. Electronically conductive component in your ACI is always bad. You always have to have the ionically conductive or insulating substance, which is always beneficial. So if you have this is attached with the lithium metal, the component are actually suitable for your battery systems, functioning system. That that's why even although the 1 order less conductivity for LPSCl compared to LGPS, this is something that most of the people use, and when can be useful for the battery system. That's why the interface is more important. And I think same for the cathode. In the cathode, whenever the cathode touch with the solid electrolyte, you always have some kind of a minor reaction happens at the interface. Now, when the cathode is fully charged, the area extension of the area, the reaction is even much higher. Okay, and then we have a lot of experiments done for, suppose for the NCA here, cathode is a NCA and the electrolyte is like Li6PS5Cl, and then if we can see a lot of, this is the LPSCl XRD, this is the XRD of the NCA, but when they mix together, there are multiple peaks are coming, and this multiple peaks nothing but all these components from brown color components when they charge together. And this is also some molecular dynamic simulation takes place. This is the NCA and this is the Li6PS5Cl, and at the interface certain time you can see lot of side product like a PO, NIS, CO, bond formation takes place. So interface has become more chaotic and more random, and then lot of product formation takes place at the interface. So the interface protection is very important for the solid state battery technology, because they are intrinsically with the sulfide electrolyte. All these oxide cathode with the sulfide electrolyte are intrinsically chemically as well as electrochemically unstable. Now let me come to the next most challenging thing on the solid state battery. For an example, let me give you. So this is the typical solid state battery. You can see this is the LiNbO3 coated NCA. So in the previous example I showed only NCA, but if you just coat a thin layer of the lithium niobium oxide on the cathode, then basically it works very well. So this is a thin lithium niobium oxide coated NCA, which is extremely good for the solid state battery. And you have Li6PS5 solid electrolyte, which I told you before. And the anode, you use either lithium metal or lithium indium alloy. Now that's very interesting. If you see, the blue one is the lithium indium alloy. When the blue lithium indium alloy is used as an anode, you have a very excellent charge and discharge graph. You can see exactly the voltage plateau, how does the NCA looks like. But once you replace your lithium indium with the lithium metal, you see it cannot charge. After a certain time the voltage getting drop, and then after like a certain times the voltage has become 0. So this is kind of a signature of the soft shortening, it has been said, and this happens when the dendrite formation takes place of the lithium. I mean, solid state battery technology, people have like speculated, or people have all over the world, people assume that okay, if it is a solid it can prevent the dendrite, but still you have dendrite into the solid state basically, and it's very challenging. Let me explain you, like there are different reasons why the dendrite formation takes place. Just very simply, let me tell you that solid liquid always wet the surface, right? But the solid cannot wet the surface. You always have like a point contact. Some of the contact is not always like a gap, like here is a gap. Okay, gap should be there. And solid always have these grains. Lot of grains are there. Now these grains, the mechanical property of the bulk and the grains are different. The conductivity at the bulk and the grains ionic conductivity are different. Okay, now when the battery cycle basically, then what happens? All these grains from lithium can deposit all these small places like where the contact is not conformal, and then from this place you can see the lithium start growing. These are the red color is the lithium. Lithium start growing, and then dendrite formation takes place, and they see the shortening takes place. So the conformal contact with the metal is very important for the solid electrolyte. This is important. Other thing also, like if you have the grain, the grain, as I told, like grain have different mechanical property, and then when you have a lithium deposit at this like a grains, then it creates a stress into your solid electrolyte, and then this stress produce crack into your grains, and this is propagate and also short the cells. Okay, and sometimes some of the solid electrolyte may have some electronic conductivity, so that in some points there is some nucleation of the lithium metal happens inside the solid electrolyte crystal or grain boundaries. So there is variable way the dendrite formation takes place into the solid state battery. For example, here is an example, nice example, which was done by the Balsara from UC Berkeley. This is the polymer electrolyte, very thin polymer electrolyte of maybe 30 micron, and you have the lithium top and the bottom. Now see, once you charge pass, you see the defect here. Very small defect here, you see, and then after certain time you see the defect is slowly increase. This defect is nothing but this polymer is getting cracked. and then lithium is growing, and then after certain time you see this whole polymer has been cracked and the lithium dendrite grows throughout the polymer and short the cell. This is what happens into the solid state battery. Okay, now there are three mechanisms usually into this kind of a dendritic growth. I won't say three, there are a lot of different mechanisms, but let me explain you the three important parameters with the lithium migration. Okay, lithium migration is nothing but when you apply some like a current density or apply some current, then how does the lithium how does the lithium ion has been dissolved into your electrolyte from the lithium metals. That depends on the applied current density. If you apply high current density, this rate will be higher. If you flux will be higher. If you apply the low current density, the dissolve will be lower. Second thing is the lithium diffusion. Once the lithium goes into your solid electrolyte, it created a defect. Okay, now the lithium has self diffusion also. So can lithium self diffused and then fill this defect. So the activation energy of this like a 50 kilojoule per mole at room temperature, which is not very high. That's why lithium can always diffuse and then the reduce the heal the defect also. The last one is the creeping. Basically, the lithium has a very low yield strength, so that's why it can creep easily even at room temperature. And lithium is also very soft. So these are the main three parameters basically which governs whether the dendrite formation takes place or not. And if you see, the creep is so important, and that's why the uniaxial stack pressure, because the stack pressure is totally control the creeping of the lithium metal. So stack pressure is one of the very important for the high quality of the battery cycling. So for an example, we have done one experiment to see. This is a typical solid state battery cells, where you can see this is a cathode, this yellow is electrolyte, and this is also anode, and you have a titanium plungers from both sides. This is a peak insulating polymers of the kind of stuff, and then this is a cell, and then underneath you have load cell. You see in the picture, this is a solid state cell, and underneath we put a load cell to monitor the pressure. Okay, and we want to see whether the the pressure really affect on the battery performance or not, and to then monitor the pressure. Now this is the normal fabrication process. Solid electrolyte, you put lithium on both sides, and then some stack pressure you applied, and you apply the some current. Okay, and then see that how does the cell work. Now surprisingly, you see that when you apply the 75 megapascal pressure, the cell instant short. So when you apply the 75 megapascal pressure, the lithium peep inside and immediately short. But when you reduce the pressure from 25, 20, 15, 10 or 5, 25 megapascal cell short around maybe I don't know, maybe 25 hours. And if 20 megapascal cell goes up to 200 hours, 10 megapascal cell goes up to like a 450 hours, 5 megapascal cell goes up to 1000 hours. So if you reduce the pressure, basically your cell longevity is getting higher and higher. This is something very, when 5 megapascal actually we didn't see any short circuit happens up to 10 hours. By the 75 megapascal, instant short circuit happens. So to understand this, what we have done basically, this is just a profile, nothing but. Okay, to understand us, what we have made a small like capillary cell. This is a titanium, and these two are the lithium, and then yellow color in between are the the solid electrolyte. We made this cell because these cells have a total diameter of the 3 mm, so that you can get a very high resolution. We did some kind of X-ray microscopic study, and then we can get very high resolution X-ray microscopy with a small time duration. You can acquire the high quality of the data. Now, when you have a 5 megapascal pressure, basically, then you do plating and stripping, and this is before and after. Before and after, you don't see, this is that titanium plungers top and bottom. You don't see any changes. These are the solid electrolyte in between. Any changes on the solid electrolytes, we can see, or any kind of changes. So that's why no short circuit happening at the lower megapascal. So the lithium migration rate, the way the lithium migrate into the electrolyte, is equivalent to the lithium creeping and the lithium diffusion. Okay, so this is extremely balanced, so that the way the lithium migrated, the same way the creeping and once the lithium migrate and produce the vacancy, the creeping and the lithium diffusion, immediately basically heal that vacancy. That's why you do not see any kind of shortening, and the any cell remains same for thousands of hours. Now when you have the 25 megapascal, you see there is a small dendrite. We see the lot of dendrite formation takes place inside the cell. Okay, where we do not see in the 5 megapascal. No. And this is happens when the migration and the creep, because it's more pressure, so more creeping, and the lithium but the lithium migration as a constant current. When this is much more higher than the lithium diffusion, then this is happens when you have you can see this kind of dendritic growth, and this is visible. Whatever you see a dendrite, basically the cell shortening, this is actually visible into your the X-ray microscopy. And then when you apply a pressure of 75 megapascal, you no need to apply current. The whole cell breaks. You can see how does the electrolyte breaks down basically, and this lithium penetrate and the short circuit happens. So the pressure is extremely important for the cell cycling. Further analysis, what we have done, we have found out whether this is really a dendrite or not. It could be anything, right? It could be. It may not be the lithium. Actually, the X-ray cannot see the lithium. We can see the only crack, the density difference. So we cannot really distinguish whether it's a void space or is it lithium. See whether it's a lithium, we need some XRD. So this is lithium XRD. You get the pure lithium metal, and this is something like okay. I said something wrong. X-ray can see the lithium metal, but X-ray cannot see the lithium ions basically. Okay, because lithium ions has only one electron only. So that's why you cannot see the lithium ions. The very less number of electrons, it doesn't diffract the X-ray. Okay, and this is the XRD of the LPS cell. Is that you see the a pure crystal structure you got here and here if you do the X-ray. Now after the shortening of the cell, if you do a pass X-ray here where the X shortening happens, you see so many peaks are there, and these peaks belongs to LiCl, Li2s, and then Li3p, and this only happens when the lithium dendrite growth and the lithium react with these electrolytes. So that gives the indirect signature that the one we have see here, these are actually the lithium dendritic growth. And then the cell which you won't able to run, these cells, this is the cell, red cell, where you cannot see any cycling data. It's just short. The same cell basically, if you control the pressure up to 5 megapascal, it can actually run the solid state battery up to you see 250 cycles. Okay, there is no run signature of the short circuiting. So that's why the pressure is very important. Stack pressure is very important for the solid state battery cycling. Yeah. Now let me come to the how long do I have? Okay. Yeah, so let me come. It's almost like a time is yeah, it's not that much time, but let me explain a little bit on the grease storage energy, grease scale energy storage on the solid state battery. So globally, the energy storage demand is getting increased, and then if you see at the end of a 2050, you will almost have a 2000 terawatt hour. Okay, but among these 2000 terawatt hour for the electric vehicles, demands is actually very less, 400. Most of the the demand is coming from the renewable energy grid. So future, mostly the battery the demands will be from the renewable energy from side of view, not from the electric vehicles. Now if we really want to replace all this demand with the lithium ion battery, is not possible, because we do not have that much lithium even on the earth core. So we have to find the alternative way, and which is the sodium. And the other side, if you see the lithium cost is also very high, it's $30,000 per ton, where the sodium carbonate is 150, and we also need the cobalt free, as I said. So cobalt free and the lithium free technology is very important for the grease storage nowadays, and which can be done with the sodium. Advantage of the sodium, excuse me. Okay, so advantage of the sodium is it is lower cost, as well as you have the plenty distributed, not like locally some places it's stored. It is distributed evenly everywhere. And then mostly US, you have a huge amount also, the people in, so the lot of labs in the US, they are very much concerned, and then research are going on for the grease storage. But the things we need for the grease storage, there is a energy density which is a 600 watt per liter. We need a very safe. All solid state battery is important. We need a lithium, cobalt and nickel free element, which are the more expensive element, and we need very long life. Normally in car, even is like a 10 years is okay. For the grid storage, we need a very long cycle life of the like a more than 25 years, and it operate from low to high temperature. Okay, and the one of the most important thing is, like, I must say, like, if when you consider like a mobile, the battery cost is like 5%. When you consider electric vehicle, the cost is like a 30%. But when you consider a grid, the most of the cost is on the battery. That's why you need something which is like a long cycle life and extremely low cost. Either you really cannot make the grid storage viable and with this kind of demand. This is just an example. As I said, the solid electrolyte, solid electrolyte, sodium is important. Here is an example that we worked on one of the chloride-based solid electrolytes, which is NYYZ, which is sodium, yttrium, zirconium chloride, and this is the parent structures, which is a very poor ionic conductivity, 10⁻⁸. But once you replace this with the zirconium, we dope zirconium from like a 0.12 to like a 0.85%. It from a solid solution basically. But once you dope from the, you see the conductivity of the bear. Once you dope with the zirconium, up to 75% doping of the zirconium, its conductivity goes almost 10⁻⁵ Siemens and 5 Siemens centimeter at room temperature, which is actually good for the battery cycling. So zirconium is nothing but the creating vacancy into your sodium system, and that's why there's a drastic enhance of the ionic conductivity. And then we studied some mechanism why this conductivity is high. One thing is, when you increase the zirconium content is higher, the volume of the atom and the channel size basically is increasing. As I told before, that when you increase the volume of the lattice, basically the ionic conductivity increase, and which is exactly happening here. When you replace the yttrium with the zirconium slowly with the different percentage, your cell volume and the channel volume increases.
Hello. Sir, we are unable to hear you. Sorry to interrupt.
Those are also localized. You can see here. It's like, but when you replace the yttrium into the zirconium, you see it's not the sodium cloud compared to the NYC has become delocalized. At the same time, you can see the chlorine also, the rotationally, like from every polyhedra, green polyhedra, which is zirconium, the chlorine is like the cloud has been like delocalized in like a rotational motion. And then we did an experiment where we froze all this chlorine, and we do not see any kind of diffusivity of the sodium. But when we let this chlorine to rotate, then you can see the diffusivity of the sodium. So this is basically, the motion of the chlorine, rotational motion of the chlorine basically help the sodium ion to diffuse. NYC, you do not have this rotational motion. That's why the sodium ions are stagnant. But the NY, when you replace with the zirconium, basically zirconium chlorine bonds is a more covalent bond, which is actually giving the more rotational the disorder into the systems, and that helps to like a sodium to move fast. It's like a paddle mechanism, like when you paddle your cycles and both sides, then the cycles goes ahead, and that is the way the conduction mechanism happens. I'll not go through all of the details, but this is one of we made a cell on the solid state battery, and then this is the one of the highest reported all solid state battery performance, which is like a almost 91.91% retention happen after 1,000 cycles with our new invention of the electric. This was not in the database. This is very fast. We invented this materials, and this gives very excellent cycle life, and I'll not go through this. And this is something we'll give you an example where you stand, like this is the circle area is something donates the current rate 1C, and also like what kind of cathode you are using. Like this is sodium chromium oxide you use, and you can see you can go up to 1,000 cycle even at the high current, which is out far from all the existing literature. And also in this you can see like the capacity retention of our system compared to cycle life is also very high. So this is something very useful, all solid state sodium ion technology, especially for the grid storage application. How long do I have, like the time? Can anyone tell me?
Yes, sir. Sir, it is almost over. We have a Q&A section also. So can we move to that section?
Yeah. So I'm not go through much details for that. Just briefly, let me tell you that I'll want to show some of the example here. That this is the okay. Okay. Okay, the video maybe is not playing, but this is just let you know this is an experiment where basically we cut the solid state battery. You cannot do this kind of experiment with the conventional liquid and battery, but in a solid state battery, basically you can cut those battery and still you can see the light. But at the same time, in the solid state battery, you can keep it up to 200 degrees Celsius and you can see still is functioning. In the conventional battery, we cannot put the battery at that high temperature. This is extremely safely hazard basically, and that is the advantage of this kind of solid state technology. I'll not go through more details. Just let me tell you this part that solid state battery also one advantage. Conventional battery, the recycling happens either the pyrometallurgy or hydrometallurgy, whether you burned everything or dissolved everything. In solid state battery, basically there is a very cost-effective recycling process are established, where basically you can regenerate every component of the battery and a very low cost compared to the conventional process. And this is also very good for the long sustainability of the solid state battery. For more details, you can go through my this paper, which is published Nature Nanotechnology, the solid state battery recycling, the process. And just let me tell you, like, I am right now a principal scientist in this, like, one of the newly established research institute called TCG Crest, where they have multiple pillars, but I'm just engaged with the RISE. RISE means Research Institute for Sustainable Energy, and the main goal of the RISE is, like, we really want something, the next generation battery technology, which is, like, the very high energy and the power density and very cost effective. We want to use the lithium metal as in liquid electrolyte, solid state battery silicon, which can able to give very fast charging, maybe 20 minutes or 10 minutes. There are various challenges, like, the 1 ampere hour pouch cell, solid state pouch cell fabrications, high loading, like 4 milliampere hour per centimeter square loading, and then novel electrolyte designing. All those things actually working, and the main application domains are like both consumer electronics, electrical vehicles, also the defense and aerospace applications at the low temperature and high temperature, the battery application, all those things basically. And we also, installing lot of state-of-art characterization tools, like from very high spatial and time resolution to, like, the very low, from nanoscale to mesoscale to macro scale, different scale. We have different characterization technique to understand and what's happening into the battery. And battery is very dynamic systems, like, once you charge and discharge, there are a lot of dynamic changes happening into the system. Most of the, our systems has been equipped with a lot of operando measurements, and most of the systems is also equipped with the glow box fabrication integration, because the battery components are extremely sensitive to the moisture also. So very state of art, like, various tools has been installed to understands, like, the more fundamentally the mechanism, the failure mechanism of the battery, so that, you can design a new material, you can design the engineer the materials much better way to have the better performance. Okay, so yeah, this is my team in UCSD where I was. And then Charlie Ming was my, and the Yoon Suk Jan and the Ogle sir was my previous mentor. And then, of course, the RISE, where I am right now, including Shell and NG, which actually funded my previous project on the solid state. So these are thanks to them, and thank you. Let me know if you have any question or anything else.
Thank you, sir. Sir, we have a quick round of some questions. So first question was, can we incorporate carbon nanotubes technology in solid state battery?
Now, where do you want to incorporate? This is, first let me be, like, the solid state battery anode you cannot use, because anode is always a lithium. Okay, because that's the way the solid state battery technology has come. If you use the same graphite or carbon nanotube into a solid state technology, then the energy density goes down, doesn't have any use. Now the carbon nanotube has an advantage. Normally what happens, the normally use the acetylene black or the carbon black. Those are small particle size of 50 or 100 nanometer. Now, these carbons are actually not good for the solid state battery. Now, if you use the very small amount of high surface area, small size of carbon, basically, then the solid electrolyte decomposed on top of the carbon surface. Okay, and this is bad. Now, instead of this small carbon dot, if you use the CNT or carbon fiber, then basically your surface area basically is lower, but your long range conductivity is higher. So the addition of this carbon nanotube or addition of this carbon fiber, which is like a high aspect ratio carbon, is beneficial for the cathode size, where you have a always decomposition of the carbon size. Addition of this kind of materials can reduces your side reaction and increase the efficiency of your battery. And some of this paper has been published from Germany, Jürgen Janek group. You can go to the group Jürgen Janek, and there is a paper called Detrimenal Effect of the Carbon into the solid state battery, where they have shown, also in one of my paper, actually, if you see my Google Scholar, that we have shown also that if you use the carbon nanofiber or like a CNT instead of the commercial carbon, the performance is much better, basically, like conductive additive.
Yes, sir. Sorry, everyone. We are short on time now. The answer to your question will be put on the Discord server. Okay.
Okay, so I'm stopping the presenting. Huh?
Yes, sir. Thank you, sir, for your valuable time.
Thank you.